what a balanced output amplifier is and why we would want to use one. Let me draw a block that represents the balanced amp. Now a balanced amplifier has a single input, we'll call it Vn, and produces two outputs that are related to the input. One output equal to a Vn and a second output equal to minus a Vn, where A is the gain of the balanced amplifier. Now you can see how the outputs are related to the input and to each other. The outputs are the negatives of each other, or you can think of them as two signals that are 180 degrees out of phase from each other. Now, why would we want to use a balanced amplifier? Say, for example, we have an electrical signal that represents an audio source. So, for example, this audio signal could be the output of an MP3 player, possibly a phonograph, and we want to transmit it through a cable or a transmission line to the next stage in our audio system. So, for example, a preamp. Well, during this transmission along this cable, electrical noise can be introduced by external electrical components, so that at the input of the preamp, we not only have the signal that we're interested in, but we have, in addition to that, this added noise component that I'm calling in. So during the transmission, we have distorted our signal that represents the audio by this external noise. But what if instead we transmit the signal using a balanced amplifier? So I make the input of our balanced amplifier the audio signal, or the electrical signal that represents the audio signal. We then transmit the signal using two transmission lines or two cables, and we make the input stage of our preamplifier a differential amplifier, a diff amp, with a gain equal to 1/2. Then any noise that's introduced due to external devices, the noise, is applied to both the AVN signal and the minus AVN signal equally. So at this input to the diff amp, we have AVN plus the noise, and at this differential amplifier input, we have minus AVN plus the noise. So then at the output of the differential amplifier, Vout, we can write that Vout is equal to one of the inputs, AVN plus the noise, minus, because it's a diff amp, the other input voltage, which is minus AVN plus the noise, all times the gain of the diff amp, 1/2. So Vout is equal to 1/2 times AVN plus AVN plus the noise minus the noise. Or the output voltage is equal to AVN. So this combination of a balanced output amplifier and an input differential amplifier tends to cancel any common mode noise that's introduced into the signal during its transmission. Now let's look at an op-amp circuit that can be used to implement a balanced output amplifier. Here is our input voltage, Vn. It's applied to the non-inverting terminal of an op-amp. We have a feedback resistor, Rf1. We have another resistor, R1, that's applied to the inverting terminal of a second op-amp, and we have another feedback resistor, Rf2. Here is one output of the circuit, and here is the second output of the circuit. Now we can consider this circuit to be composed of two simpler op-amp amplifiers, a non-inverting amplifier and an inverting amplifier. Remember, these two voltages must be equal to each other. The voltage here is ground, which means the voltage at this node is 0 volts or ground. So we can consider this portion of the circuit to be a non-inverting op-amp amplifier with a gain of VO1 equal to 1 plus Rf1 over R1, and we multiply that by Vn to get the output voltage, VO1. Now, this voltage here must also be equal to the voltage here, so the node voltage here is equal to the input voltage Vn. We can consider this circuit, or this portion of this circuit, to be an inverting op-amp amplifier with an input voltage Vn. So VO2 is equal to negative RF2 over R1 times Vn. Now, what I want to do is design this circuit so that it meets a couple of conditions. One, I want the magnitude, let me write design. I want the magnitude of the gain A of this balanced output amplifier circuit to be equal to 6. And I want to impose a second condition, and that is that I want the maximum current through RF1 and RF2 to be 1 milliamp when the magnitude of VO1 is equal to the magnitude of VO2 is equal to 12 volts. So you can see that from these two equations we can impose this gain condition. We can choose RF1, RF2, and R1 so that the gain here is equal to 6 and the gain here is equal to negative 6. But to implement this second condition, we need another equation, an equation for the current through RF1 and RF2 in terms of the circuit component values. Now, remember, there's no current into the input terminals of an op-amp, so the current into this inverting terminal is 0, and the current into this inverting terminal is 0. So any current that flows through our RF1 must also flow through R1 and flow through RF2, because there is no way out at this node because of the infinite impedance looking into the op-amp here.
Saluditos, cachetes, no. Gracias por pasar a saludar. Siempre pasas a escribir. Gracias.
And there's no way out at this node because of this infinite input impedance. So we have flowing from here a current that flows through RF1, through R1, and through RF2. So I can use Ohm's law to calculate that current. The difference in voltage across this series combination of 3 resistors must be equal to the current through the resistors times the resistance. Or in other words, I can write that VO1 minus VO2, the total voltage across the 3 resistors, divided by the sum of the 3 resistors, the series resistors, RF1 plus RF2 plus R1, must be equal to the current I through the 3 resistors. So, to impose our second design condition, I can write that VO1, when it is equal to 12, minus VO2, which is equal to minus 12, divided by RF1 plus RF2 plus R1 must be equal to 1 milliamp. Then we know that 1 plus RF1 over R1 must be equal to 6, and we know that minus RF2 over R1 must be equal to minus 6. So this equation implies that RF1 is equal to 5 times R1. This equation implies that RF2 is equal to 6 R1. So I can use these two equations to eliminate RF1 and RF2 from this equation. So I can write that 24 divided by 5R1 plus 6R1 plus R1 is equal to 1 milliamp is equal to 24 divided by 12 R1, which implies that R1 is equal to 2 k-ohms. Then I can use RF1 is equal to 5R1 is equal to 10 k-ohms, and RF2 is equal to 6R1 is equal to 12 k-ohms. So if we construct a balanced output amplifier using these resistor values, we'll meet our design specifications. Welcome back to Electronics. This is Dr. Robinson. In this lesson, we are going to solve for the branch currents in a differential amplifier circuit. Here is a schematic of the circuit we're going to analyze, and I have labeled the currents that we're going to solve for as we proceed through the example, I1 through I7, plus the load current IL. Now let's begin by solving for the most apparent branch currents in the circuit, and those are I3 and I4. You can see that I3 and I4 are the currents into the input terminals of an ideal op-amp. So we know immediately that I3 must equal I4, must equal 0 amps. Now let's find the current I1. We know that I3 is equal to 0, so the current that flows through the 4K resistor must also flow through the 16K ohm resistor. So we know that we have a total of 10 volts from ground to this node, or a total of 10 volts across the series combination of the 16K resistor and the 4K resistor. So I can use Ohm's law to solve for I1. I1 is equal to 10 volts, the voltage across the series combination of the 16K and the 4K resistor, which is equal to 10 over 20 milliamps is equal to 0.5 milliamps. Now, again, because I3 is equal to 0, we know that the magnitude of I1 must equal the magnitude of I6 because they're the same current, but I6 is defined in this direction. So we can write that I6 is equal to negative I1 is equal to negative 0.5 milliamps. Let's now find the current I2, and we'll begin by determining the voltage here at the inverting terminal of the op-amp. We know we have an op-amp circuit with negative feedback, so the non-inverting voltage here must equal the inverting terminal voltage here. And we can solve for the voltage here by voltage division. So let me write that V plus, the non-inverting voltage, must be equal to the inverting terminal voltage is equal to 10 volts times this voltage divider. So 16K over 4K plus 16K is equal to 10 times 16 over 20, or 80% of 10, or 8 volts. Now we used voltage division here. Another way to solve for the non-inverting terminal voltage would be just to multiply the 16K ohm resistor by the current through it, which is a half a milliamp. So 16K times a half a milliamp would be equal to 8 volts. So we now know the voltage here at the inverting terminal is 8 volts, and we know the voltage here is 12 volts, so we can use Ohm's law to solve for the current through this 4K ohm resistor. So I can write that I2 is equal to 12 volts minus 8 volts divided by 4K is equal to 4 volts over 4K is equal to 1 milliamp. Now, I4 is equal to 0, so the current that flows through the 4K ohm resistor must also flow through the 16K ohm resistor because there's no way out at this node. So I2 must be equal to I5. So I2 is equal to I5 is equal to 1 milliamp. Now I want to solve for the load current IL, but to do that I'm first going to solve for the voltage Vout, because I can divide Vout by 2 k ohms to get IL. And I'm going to solve for Vout by beginning with this known voltage here at the inverting terminal, 8 volts, and then I'm going to subtract from that node voltage the drop across this 16 k ohm resistor. So this voltage minus this voltage drop would give us the voltage at this node, which is equal to the output voltage. So I can write that Vout is equal to 8 volts, the voltage at the inverting terminal, minus 16 k ohms times the current through the 16 k ohm resistor, which is I5, which is 1 milliamp. 1 milliamp is equal to 8 minus 16 volts is equal to negative 8 volts. So we can now solve for the load current IL using Ohm's law as the output voltage divided by 2 k ohms. So IL is equal to negative 8, the output voltage, divided by 2k is equal to negative 4 milliamps. Now the load current is defined in this direction, but this negative sign indicates that the actual load current is flowing in the opposite direction. So if we have negative 4 milliamps flowing in this direction, then we can think of that as 4 milliamps flowing in this direction. So we have 4 milliamps into this node from this direction. We know we have 1 milliamps flowing into the node from this direction. So the total current in this branch flowing into the output of the op-amp is 4 plus 1, or 5 milliamps. And we can see that I7 is defined in the other direction, so I7 must be equal to negative 5 milliamps. Or we can solve for I7 using an equation. We could write that I7 is equal to IL minus I5 is equal to negative 4 minus 1 is equal to negative 5 milliamps of current. Now, in solving for the output voltage in this problem, I use this known node voltage and the drop across this resistor. But another way to do it is to use the known result for the gain of a differential amplifier, if we recognize that this is a diff amp. These two resistors are equal, and these two resistors are equal. So we can write that the gain of this diff amp, let me write it here, Vout is equal to 16 divided by 4, 16 the value of these two resistors, and 4 the value of these two resistors, times the difference of the input voltages. The 10 volt source is applied to the non-inverting terminal, and the 12 volt source is applied to the inverting terminal. So we write it as 10 minus 12 is equal to 4 times a negative 2 is equal to a negative 8 volts. The same answer we obtained before. Welcome back to Electronics. This is Dr. Robinson. In this lesson, I want to work an op-amp example problem where we solve for the output voltage of an op-amp circuit. Here's the schematic of the circuit we're going to analyze. Here's the input voltage. Here's the output voltage of the circuit. It's a 2 op-amp circuit. Let's begin by noting that the voltage at the inverting terminal of this op-amp is equal to the input voltage. So the voltage at this node, because of the ideal op-amp, must also be equal to Vn. We can calculate the current I through this R4 resistor as Vn divided by R4. So I is equal to Vn divided by R4 is equal to V plus the voltage at the non-inverting terminal divided by R4. Now, to calculate the voltage at this node, let me label it V01, the output voltage of this op-amp. We'll start with this node voltage and add the IR drop across R3. So I say that V01 is equal to V plus the voltage at the non-inverting terminal plus I times R3 is equal to Vn plus Vn over R4 times R3. Now let's introduce Vout, the voltage we're trying to solve for, into our set of equations by writing a node equation at this node. So I can write that V01 minus 0 over R2, the current through this resistor, plus V0 or V out, minus 0 over R1 is equal to 0, which implies that VO1 over R2 is equal to negative V out over R1, or VO1 is equal to negative R2 over R1 times the output voltage V out. Now, we know that VO1 is equal to Vn plus Vn times R3 over R4, so I'm going to make that substitution into this equation. So I can write that Vn plus Vn times R3 over R4 is equal to negative R2 over R1 times the output voltage V out. Now, on this side of this equation, I can factor Vn out, bring it to this side, to solve for the ratio of V out to Vn, or the gain of the circuit. So I can write that V out over Vn is equal to negative R1 over R2 times 1 plus R3 over R4. The answer. Now let's rework this problem in another way, where we use known results to simplify our analysis. Now we recognize that this portion of the circuit is an inverting op-amp amplifier, so we know the relationship between VO1 and V out. VO1 is equal to negative R2 over R1 times V out. Then we recognize this portion of the circuit as a 2-resistor voltage divider, where the output voltage here is equal to the input voltage times R4 over R3 plus R4. And because of this ideal op-amp, we know that the voltage here must be equal to the voltage here, which is equal to Vn. So we can write by inspection that Vn over R1 times V out. Now let's rework this problem in another way, where we use known results to simplify our analysis. Now we recognize that this portion of the circuit is an inverting op-amp amplifier, so we know the relationship between VO1 and V out. VO1 is equal to negative R2 over R1 times V out. Then we recognize this portion of the circuit as a 2-resistor voltage divider, where the output voltage here is equal to the input voltage times R4 over R3 plus R4. And because of this ideal op-amp, we know that the voltage here must be equal to the voltage here, which is equal to Vn. So we can write by inspection that Vn is equal to V out times negative R2 over R1 times R4 over R3 plus R4, where again, V out times negative R2 over R1 is equal to VO1, and VO1 is the input to the voltage divider with a gain of R4 over R3 plus R4. So VO1 is this portion. We multiply by the voltage divider to get the voltage here, which is equal to Vn because of this ideal op-amp. Then we can write that VO is equal to, or VO over Vn is equal to negative R1 over R2 times 1 plus R3 over R4. The same answer we obtained previously. Now let's look at something to note about this circuit. It may appear at first that this circuit does not have negative feedback, and because of that we cannot consider the voltage at the inverting terminal to be equal to the voltage at the non-inverting terminal. You can see that there's no path from the output voltage to the inverting terminal. In fact, there's a path from the output voltage to the non-inverting terminal, which may appear initially to be positive feedback. But in this path between the output voltage and the non-inverting terminal is an inverting op-amp that introduces a negative sign. So this path from output to non-inverting terminal is actually a negative feedback path, and because of that, the voltage at the inverting terminal is equal to the voltage at the non-inverting terminal.